Look closely at this cinematic shot. This is the final, perfectly synchronized output of the Volts and Ventures AI production engine. To get here, the system takes a raw text script and passes it through two distinct generation models. Qwen2 constructs the video, and Qwen3 TTS synthesizes the voice. Firing up a local Python script to trigger an AI model's API is simple, but trying to orchestrate a continuous, multi-model production pipeline on a serverless GPU environment breaks almost immediately. This diagram shows the baseline architecture a developer typically builds first, a simple local script node firing raw API requests directly at a remote Hugging Face space endpoint. But at scale, this naive approach collapses under dependency locks, memory constraints, and continuous routing errors. Robust MLOps is not about model selection. It requires deconstructing these specific deployment failures to engineer a resilient, hybrid client-cloud architecture. The first major stack trace in our deployment was a 401 unauthorized error. Instantly, the system exhausted its tiny 2-minute daily compute quota. The root cause was a single uppercase letter. The Hugging Face API strictly requires access tokens to begin with a lowercase HF_. The script was submitting an uppercase HF_. This diagram illustrates the consequence. Because the token format was rejected, the API gateway demotes the client to an anonymous guest. That forces the system to share a tiny global compute pool, which drains from 100% to 0 in a fraction of a second. Even after formatting the token correctly, the local client crashed again, returning a parsing exception that read, "Expecting value line 1, column 1, character 0. This is a classic Gradio routing trap. Sending raw HTTP calls to an unregistered port 7860 on a Gradio server doesn't return a JSON payload. The server returns the raw HTML of its front-end web interface instead. When the local JSON parser attempts to read that raw HTML response, it throws a fatal exception. To bypass this routing trap, we abandoned raw HTTP calls entirely. The new architectural standard mandates that all local communication tunnel through the Gradio client using its native remote procedure call protocol, and requires the container metadata to explicitly declare the Gradio SDK. Secure, automated API pipelines require strict client-side typing and native protocol tunnels to survive beyond the prototype phase. Moving to the remote cloud server build phase, the pipeline encountered a fatal Docker container error. Dependency resolution exceeded maximum depth. Look at this container diagram. The Hugging Face 0 GPU build environment automatically pre-injects and pins core machine learning frameworks directly into the base image. When a user uploads a requirements file including these same pre-baked libraries, the new dependencies conflict with the base image. The pip package manager attempts to reconcile the strict pinned ML libraries against the rigid base environment, entering an infinite loop that eventually crashes the build. This danger is compounded by Linux's strict case sensitivity. A single ghost file named requirements.txt with a capital R can quietly poison the entire resolution process. The architectural fix for this issue is aggressive pruning of the requirements file to prevent these build tree locks. The strict rule for serverless dependency management is to omit all pre-baked 0 GPU frameworks entirely and leave only loosely bounded utilities. Heavy, conflicting libraries must be isolated and installed at runtime using a no dependencies flag directly inside the main application script. This streamlined strategy protects the base environment from version conflicts and allows the Docker build to complete in seconds. In serverless MLOps, duplicating base dependencies destroys the container before inference can even begin. The final category of crashes happens during startup and memory allocation, beginning with the error nospaces.gpu function detected during startup. This diagram shows how 0 GPU handles dynamic hardware leasing. It strictly requires explicit decorators placed on top-level global functions in order to detect and slice NVIDIA hardware. To satisfy that requirement, you might instantiate massive model weights like Qwen2 and Qwen3 at the very top of the script. But this cold start approach, loading all weights simultaneously during module import, causes an immediate VRAM out-of-memory crash. The MLOps solution is lazy loading. Model weights are instantiated dynamically and strictly inside the processing handlers, so they only consume VRAM when requested. With the infrastructure stable, the next challenge is algorithmic directing, enforcing precise temporal synchronization between the video clips and the audio tracks. Generating the video first is a mechanical flaw. You cannot easily stretch or shrink the non-deterministic pacing of generative video to fit a specific line of dialogue. The pipeline solves this using an audio-first back-timing matrix. Step 1. Synthesize the voiceover audio track first and measure its exact physical duration in seconds. Here we see Step 2. We feed that precise audio duration into a mathematical formula to calculate the exact target video frame count, enforcing perfect synchronization. True algorithmic directing ultimately relies on strict mathematical constraints to enforce pacing on inherently chaotic generative AI models. From those 10,000 crashes emerges the final, hardened Volts Inventures architecture, a tiered, highly resilient client cloud pipeline. Look at the left side of this map. The local level controller is responsible for handling JSON iteration, orchestrating API routing, and managing the final media assembly via FFmpeg. This local client handles the fallback cascades, ensuring production never stops if cloud quotas run dry. On the right side, the remote level server manages the heavy fast API and Gradio backend, zero GPU hardware allocation, and the lazy loaded model inference. This creates a distinct bifurcation in engineering requirements. Junior-level scripting handles the local state and routing, while senior MLOps engineering is required to deploy and maintain the remote cloud server. Every robust component of this automated pipeline was engineered as a direct response to a catastrophic deployment failure. Deploying production AI at scale requires orchestrating asynchronous state, mastering dependency environments, and engineering resilience. And when all of those critical elements are finally secure and locked firmly into place, the autonomous machine simply runs.